everybody. I'm getting sick of doing problems at my desk. And I bet you're getting sick of watching me do problems at my desk. So I threw this one on the board. I needed a little exercise. I feel like it brings us back to the old days. Hopefully, the soon-to-be future days of you guys sitting in class and us working on problems together. So here it is. I put two charges on a number line. And I started that number line all the way down at 0. 1, 2, 3. And at 4 meters, I placed a +3 Q charge. As I sit here, I realize, you know what? I'm going to make that a +3 nanocoulomb charge. 5, 6, 7. At 8, I placed a -1 nanocoulomb charge. And here's what I'd like to do. I'd like to answer these two questions. What is the potential at point P? And also, where is the potential equal to 0? And we're actually going to limit that to just one of the two places where the potential is equal to 0. So, where is point P? Good question. Let's make 2 meters at 2 meters our point P. Go ahead. So, if you haven't already written this problem out on the top of a nice clean sheet of paper, do so now. Here we go. To find the potential, you guys know that potential is simply the voltage, which for a point charge is going to be kq over r. And I know that you know it's a scalar, which means we're not worried about the direction, just the magnitude. But because that magnitude can be positive or negative, it's all about including the signs. So, to find the sum of the potential caused by these two charges, the sum of the potential would simply be V1 plus V2. Let's go ahead and substitute in. So the sum of the potential would be KQ1 over R1 plus KQ2 over R2. This is easy. All right, let's keep going. All right, so I've got K is 9 times 10 to the 9th. I hope that you can see this. In fact, I'm going to zoom in. Look at the magic of that zoom. Times +3 times 10 to the -9 divided by the distance 2 plus the potential caused by the -1 charge. So 9 times 10 to the 9th, -1 times 10 to the -9. Oh, negative divided by that distance. Wait, how far is it? That's right. 6 meters away. So, what I'd like you to do is to take a moment and plug that into your calculator. What I end up with? Anyone else plug that in? I believe this would be positive 13.5, negative 1.5. So I should have ended up with the sum of the potential at that point is 12 volts. Now, honestly, I'm sure you guys just went 27 divided by 2 is 13.5. -9 divided by 6 is -1.5. Nice job, everybody. Good for you. Now, where is the potential equal to 0? I think it's very obvious that somewhere between these two charges, the potential would go to 0. Because as we approach this +3 charge, that potential is going to skyrocket because it's related to the inverse of the distance. So it's going to become asymptotic right there until we get right to the charge. And then here, the same thing is going to happen in the negative direction. So if these are our 2 points, clearly it's going to go through the x-axis some point in between here. So I'm just going to go ahead and label that with an x. So let's go ahead and find that. Now, I think I might need to zoom out slightly. Ah, the magic of technology. Or just moving the tripod. Now, when we did these problems with electric field, this was a serious pain in the neck. But when we're looking for just the potential, it's not. The sum of the volts is going to be equal to 0. Now, the sum of the volts I'm going to work right below is going to be plus V1 plus V2 equals 0. The sum of. Add them up. It's only now when I plug in plus KQ1 over R1 plus KQ2 over R2. I have to kind of stop and think for a moment. I see that the K's are going to cancel out. I also see that I have 2 unknowns, R1 and R2. So what we've been doing is that if it's in this region in between, this distance would be R1. This distance would be R2. Yeah. So R1 plus R2 is equal to, 4. Therefore, R2 would simply be 4 minus R1. How about we substitute that in? So I'm going to show that down here. Now, don't lose focus. If we keep going, I'm going to have plus 3 nanocoulombs over R1 equals, do you see it? I'd like to pretend that I was faking it so you would catch my mistake, but I wasn't. Right here, when I added these two together and got 0, and then all of a sudden, I brought this to the other side, what did I lose? Besides my mind. There should be a negative sign there, introduced by the algebra. So I'm going to have negative 1 nanocoulomb divided by 4 minus R1. Oh, I see it too. The nanocoulombs cancel out. And this math becomes pretty simple. Cross multiply. Fair enough? Good? Distribute. Math. Add the 3R1 to both sides. Oh, wait a minute. Add the 3R. Oh, wait a minute. Does this mean I have to start the whole problem over? Or have some of you been screaming at your computer right now saying, no, Mr. Edgar, don't do it. Don't do it. I did it. Down here, there's a negative sign. This negative sign was introduced algebraically by subtracting it to the other side. But that charge right there is also negative. So at this step, what I should have plugged in was a negative 1 nanocoulomb. So that when I cross, whoop, whoop, bam, bam. Now when I add it to both sides, add the 3r over, I end up with 4r1. So 12, I add that over, I get 12 equals 4r1. So r1 equals 3 meters. Or at the 7-meter mark. Now, what was I doing right there? I was doing my best to demonstrate the common mistakes that students make when they're solving these problems. It's all about the signs. It's all about being careful with our algebra and making sure that we plug in the sign of the charge because it's a scalar quantity. And in the end, it turns out that my spot where it would be equal to 0, right there. If I wanted to, which I don't, not right now, I could also find what spot in this region would the potential also be equal to 0. I might just step aside. So, you thought I was done. So did I. And then I realized I should ask you one more question while I have you here. Here it is. How much work must be done by an external force to place a proton at point P from really far away? Now, really far away is really far away. So based on just these 2 point charges in the universe, really far away in a galaxy far, far away, what would be the potential caused by these two if we zoom down? Yeah, that's right. That potential would be 0. So the work done by an external force to bring a proton, charge Q, to that potential would be work equals Q delta V. Now, just this one time, I'm going to write it out as voltage final minus voltage initial. And when I see that, the final potential at point P was 12 volts. The initial potential, is 0. And the charge on a proton, 1.6 times 10 to the negative 19 coulombs. So the work done by an external force would be, hey guys, don't pick up your calculators, I got you. 1.92 times 10 to the negative 18 joules. You know what that means? That means that the proton, when placed there, would have 1.92 times 10 to the negative 18 joules of potential energy. Now that positive charge, when I release it, what's going to happen? That potential is going to be converted into kinetic energy as the electric field does work on the charge. So it doesn't matter where this charge started from far away or what path it takes. As I apply a force to it to bring it to point P, what really matters is what is the change in potential from very far away to that point. One last thing. Keep finding myself saying that a lot. 1.92 times 10 to the minus 18 joules would be equal to 12 electron volts. I want you to think about why that's so simple for me to come up with. And we'll talk about that next time. Now. Cut!